So hello, everybody, and welcome to the IIAS Program on Analysis and Graphs seminar. I would like to ask the people here, if you have a question, please wait for me to give you the microphone so that people over Zoom can hear your question. Okay? That's a serious...
The warning is recorded so that if someone doesn't do it, that like everyone will know.
Yes. So we are very happy to have Yishai Lavi today with us, and he will tell us about projective geometries over finite rings.
Okay. Thank you very much. Thank you for inviting me to speak here. So I want to open with a note regarding the title, Projective Geometries over Finite Rings. So I forgot for a moment who said it, but there was someone who said about math that like we needed to give a serious and difficult titles to our work so that people will take us seriously. So this title, which looks and sounds probably quite scary and not very intuitive, is not revealing how nice and simple the talk will be. Okay, so I just put it here so like so that everyone who watches the first 10 seconds will see it. Well, here's a serious man, but you know it's going to be much more simple. And what I want to do. So everything I'm going to talk about is a joint work with Ori Pauzanchevsky, Professor Ori, my supervisor. And what we're going to talk about is a family of very nice graphs. And the story of how I came to study them is that I came to Ori and I asked what do these think I can study, I can research, and he told me, you know, there is a nice family of graphs that I studied with Professor Tali Kaufman in Bar Ilan, and we wrote an article about it. And it turned out that like they worked over a very complicated graph, and they managed to reduce the problem to a very simple graph. And he told me we managed to prove what we wanted to prove regarding the simple graph, but the proof wasn't very elegant, and it wasn't very structural. It was like a double induction and stuff like that. It's like 2 pages, very scary. Don't open it. And he suggested maybe you can try to study this complex, this graph, and maybe you'll find a nicer proof to it, and a nicer proof to what we wanted to show. Basically, they wanted to calculate the spectrum of the graph. So that's both the motivation there and also the motivation of me coming here. And then we calculated the spectrum, and we showed that the spectrum is independent of many important variable of much of the algebraic origin of the graph, but rather it depends only on a few numeric properties. And then we said, oh, okay, so it turned out that we will have, I'll in a moment get into more details, what is the graph, that will take the most part of the first hour, like to explain what the graph is. But it turned out that there are many similar graphs that have the same spectrum. And then we asked, okay, so are they also isomorphic? The first question one should ask when he reaches this kind of situation. And then we tried to, and we checked like on Sage, and we saw that there are a lot of graph theoretic properties that are the same indeed that are invariant between both of them. But we tried to calculate the automorphism group of the graphs, and it turned out also to be a very nice thing, and it helped us distinguish between different similar graphs. And that's mainly what we did. That's mainly what I want to propose here. So what I'll do now in the first part of the hour will be to give an introduction and to describe the graph that we're studying, which is very nice, and I won't explain why we're studying because it's just a very nice graph to study. And then I'll state our results, and then I hope in the second hour to touch main concepts in the proofs. Okay. So I'll start with an example without even stating an example for what it is. But we'll start from an example, and the example will be the funnel plane. And the funnel plane, as I assume probably most people here know, it's a what one can say, it's a description of 7 points and 7 lines, such that every line contains 3 points and every point is contained in 3 lines. And there are many nice things about the funnel plane. One thing about it, one of the ways one can describe it is as the set of lines and planes, and F2 to the third. So we have a vector space of dimension 3 over F2, and we look at the set of all the lines, which are the one-dimensional subspaces, and the planes, which are the two-dimensional subspaces. And the dots here represent the lines represent the planes, and everything here works very nicely. But I don't want us to think about the set of lines and planes in this way. Rather, I want us to think about it in a different way, and that is we have 7 points. This will be a more, in a way, like a more graph theoretic approach to it. So we have 7 points representing the lines. We have 7 points representing the planes, and we'll put an edge between a line and a plane if the line is contained in the plane. Okay, so it's an undirected graph. And one can do such a thing about not only F2, rather a general field. So we'll now give a definition. Well, the cap doesn't stay on the marker, but what we're going to define definition. So let F be a field. So in our case, we're going to work only over finite fields. So all right, let F be a field. The projective plane over FP is a graph whose vertices are subspaces, strict subspaces of FP to the third. So we have lines and we have planes with edges corresponding to inclusion. Corresponding to inclusion. Okay, so this is the first concept I want to introduce. That's the projective plane. It's a graph. It's a bipartite graph. It has non-trivial subspaces. Non-trivial subspaces. It's a bipartite graph. It has lines. It has planes. It has edges corresponding to inclusion. And one can already ask a natural question: what's the spectrum of this graph? No, it's an undirected graph. I have an edge between a line and a space if the line is contained in the space, if the plane is containing the line. And one can ask, what's the spectrum? So 1 second, I'll give the notation so we know. Notation. We will write it P2 FP. Okay. So a classical question, a classical example in expander theory, which is something I'm not going yet to talk about it. I hope to get it later in the lecture. But a standard result in expander theory is to show that this graph has a very nice spectral expansion. What it means is just that the ratio between the two first eigenvalues is nice. It's pretty low. It's pretty small. And in general, what we do in this exercise is to fully calculate the spectrum of this graph. And how would we go about it, to calculate the spectrum? So, question, what is P2 of FP, the spectrum, sorry. What is the spectrum of this graph? So what we'll do, the approach that we're going to use is to look at the squared graph. Okay, so we denote by G the squared graph. So any bipartite graph when we're looking at the squared graph, has now two connected components. So in our case, we have one connected component corresponding to the lines. Oh, the squared graph is just the graph with an edge corresponding to a path of length 2. A walk of length 2 on the graph. So two edges are now two vertices are now adjacent if there is a path of length 2 between them in the original graph. Yeah, and we delete the original edges. It's the same as looking at the adjacency matrix squared. Yeah. Yeah, the spectrum, I mean yeah, exactly. The spectrum of the adjacency matrix. So we denote by G the squared graph, and now we have two different connected components, one corresponding to lines and one corresponding to planes. Okay, and a standard result in linear algebra shows that it's enough to calculate the eigenvalues of one connected component, and the eigenvalues will be the same. Okay, so it's enough. Yeah.
Much bigger.
Oh, okay. Yeah. Well, okay. Yeah, it's very small. Okay. Okay, so what we do? Yeah. Yeah, okay. So what we do is we denote by G the squared graph, and it's enough to look at one connected component. Okay, to look at one connected component. So what's one connecting component here? We have as vertices all the lines, and we're asking what lines are adjacent to each other. So what would it mean for two lines to have a path of length 2 between one and the other? It means that there is a plane connecting them. So when we're looking at the squared graph, we're allowing also multiplicity. So there can be many walks, many edges now between vertices. There can be loops. All right, so in our case, we know that there is a squared edge between two lines if there is a plane containing both of them, right? And that holds always, right? Any two lines will have a plane containing them, and we know that there is exactly one plane containing them. And how many planes, if we ask for a given line, how many planes contains that given line? So we won't go over it now, but it's p+1. So there are p+1 planes containing the given line. All in all, if we now describe the matrix corresponding to lines. Okay, so we have here L1, L2, all the lines. So how does the adjacency matrix, when it's squared, how does it look like? So along the diagonal, we have the amount of loops between L1 and itself, between a line and itself. So it's p+1. Sorry, I'll write it larger. Okay, so we have along the diagonal, we have p+1. And anywhere else, we have ones, right? Because between any two distinct lines, there is exactly one plane containing both of them. So we have here a matrix. It's very easy to calculate the eigenvalues of it. The eigenvalues are p squared plus 2p plus 1 and p, and lots of p's. So now we take the root of this set, and we get the eigenvalues of the original graph. Okay.
So this matrix is the adjacency of 12 graph.
Yeah, when we're restricting ourselves only to look at lines. Yeah. Yeah, exactly. And what I said is that it's a pretty standard result in linear algebra that if we have like a block matrix of the sort AB, so when we look at the squared matrix, it's enough to calculate. So the squared matrix will be something, I'm not sure about the order, but it will be something like AB, BA, 0, 0. So it's enough to find the spectrum of just one.
AB is what you want.
Yeah, exactly. Exactly. So if so in a way, like this is the larger matrix, and here I didn't write it out. Okay, so.
Yeah, okay, yeah. Good. Yeah.
Okay, so now we don't have to work over a plane. We can also work over any projective space, and that is if we, instead of working only non-trivial subspaces of fp to the third, right, we can work over fp to the n, or fp to the power of d. So the projective space PD, we'll call it PD minus 1 fp, is a graph whose vertices are non-trivial subspaces of fp to the power of d, with edges corresponding to inclusion. Okay, so this graph is not bipartite at all, right? It has a lot of layers. It has d minus 1 layers. So in some sort of sense, one can think about it as we have here a lot of vertices, and here a lot of vertices, and here a lot of vertices. So this is all the subspaces of dimension d minus 1. This is all the subspaces of dimension d minus 2. And here are all the lines. So it's a d minus 1 partite graph. It has d minus 1 I forgot now the name. Like there aren't edges between any two vertices in the same row, but it has like a lot of vertices of this sort. So one can also make this graph a simplicial complex by looking at the flat complex, but I don't want to another word. Like I don't want to go over it now because it will take us too much time, and it's not very important. What we're doing here, so this graph is a classical graph that one can think about it. It's very interesting. Like naturally, when one thinks of graph theory in the context of linear algebra and vector spaces, so this is a question one can think about. One can ask, what is the spectrum of this graph? It's not simple. It's not at all simple to show it. What we wanted to discuss a little bit different graph. And to do that, I want to introduce the concept of rings and modules. So it won't take too much time, but it won't take too much time, mainly because I want to focus on a specific concrete example, which is much simpler than the general theory. So a ring, I assume that this is something everyone here knows, is like a field, but the multiplication is a little bit nice. It's a little less nice. I mean, not every element has an inverse. The multiplication isn't necessarily commutative. Yeah, sorry, I didn't write it correctly. It's not the projective space, it's the projective geometry. Yeah, sorry. Okay, this is just a name. Okay, so again, we have a field, and if we let the multiplication be a little less nice, then we get a ring. And in our case, I want to focus on a specific family of rings of the kind z over p to the power of r z. Okay, so what we have here is just the integers 0, 1 until p to the power of r minus 1. There are p to the power of r elements with multiplication and addition modulo p to the power of r. And now this ring, so the multiplication is commutative. It's much nicer than the general case. And one can now ask what's a module over this ring. Okay, so we have the ring, we'll call it OR. Okay, we just define it to be Z, the p to the power of R.
P is not prime?
Yeah, P can be a prime power, but no, P is prime. In our case, P is prime. Okay, so we're working over the set of integers 0 until p to the power of r minus 1, with p being a prime number. And a module over this ring is exactly like a vector space, but instead of working over a field, we're working over this ring. Okay, so we have, let's say M is a module over OR. If it's looking, so I'm a bit of I'm not specifying everything here exactly formally because I mainly want like to get to the point of what we're talking about. So M will be isomorphic like a vector space, like with coordinates, with the coordinates A until AT for some T with AI coming from OR. And we can add vectors, we can multiply vectors by elements from the ring. Okay.
So it's finite dimension.
Yeah. We're working here over finite dimensional stuff. Everything here in general will be finite, both the rings and the dimension. Yeah. It's everything here should be nice. If something doesn't look nice, then ask. And what we're now going to define is the projective geometry over this ring. But before that, I want to note a few aspects of this module. This module, which is of dimension or rank T over OR. So first we know that OR not all the elements are invertible. Not only that, there are zero divisors, right? Or there are even nilpotent elements, right? Because P to the power of R, we have P is in OR, and P to the power of R is 0. So not only P isn't invertible, it's a zero divisor, and it's nilpotent. And in general, any element here which can be divided by P, right, is not invertible and it's nilpotent. So if we look at vectors here, and we now want to look at the module generated by this vector. So the module generated by a vector V is exactly like in linear algebra. It will just be OR times V, which is the set of all AV with A coming from the ring. Okay, and sometimes this might be isomorphic to the ring itself. Sometimes it might be much smaller, right? Because let's say we take T to be 2, and we now have the module M A1, A2, and we'll look at the vector 1, 0. Okay, V is 1, 0. So the module generated by V is just all the elements of the type A0, which is isomorphic to the ring itself, right? But if we look, if we take V to be something else, V prime to be P0, so the module generated by V is not all the elements of type A, rather only all the elements of the type P to the power of A. So how many elements we have here? We have P to the power of R minus 1, right? Because we have only the elements which can be divided by P. And in general, one of the questions we're going to ask, which we're going to discuss a lot during this talk, and regarding the complex of the graph that we're going to define, is how do the modules look in this case, in this scenario? So we have modules that are isomorphic. So we can have a module which is isomorphic to OR to some power. And we can also have modules which aren't isomorphic, which aren't isomorphic to any power of OR. So we will call a module which is isomorphic to OR to the power of T a free module. Okay, and a free module will behave exactly like vector spaces over a field. However, in our case, we also have non-free modules, which we will have to tackle around a bit differently. But what is nice is that we're going to define our graph So definition, the projective geometry P to the power of D minus 1 OR is the set is a graph, is a graph, again, whose vertices are free, non-trivial submodules of OR to the power of D. Okay, so the world we are working in, like in the case of the projective geometry over a field, we worked over a vector space of dimension n or of dimension d, and then we looked at all the subspaces, all the strict subspaces, and we looked at, I didn't write about the edges, and edges correspond to inclusion. So on the one hand, we now made things a bit more complicated because we're not working over a field anymore, rather over a ring, which has some elements which are zero divisors, which are nilpotent. But in any way, when we're defining our graph, so we're like taking a step back from the complication that we've done, and we're looking only at the simple and nice stuff that we have, only at the free submodules. And again, the free submodules are exactly what we would expect when we're working over fields and over vector spaces, because right, one of the most basic lemmas in linear algebra is that any subspace of a vector space is itself a vector space, and it's isomorphic to f, in our case, to f to the power, to some power. So we're looking only at submodules which are themselves look like OR to some power. Okay, so I'll give like a short example. So if we take P and R to B2, to P and R and D and D minus 1 all to B2. Okay, so what do we have here? So our general model, so we have Z over 4 the power of a third. That's the original module that we're working over. And we're looking at free subspaces. So we have subspaces which correspond. So this is, let's say, our module. And we have submodules isomorphic to Z over 4Z, and submodules isomorphic to Z over 4Z squared. Right, if it's Z over 4Z to the cubed, then we already get the whole module. And again, this module M, it contains much more submodules. It has more sets that are closed under multiplication, under scalar multiplication and addition, but right now we're not going to, I don't know, to refer to them. Yeah, excellent, thank you.
Then the students are kind of nicer. Then you have like that's why you take.
Yeah, so the motivation to take them. So there is a there are two main motivations to define it in this way. So one way is that the places where this graph arises more naturally in the quotients of the Breuer-Stitz building, it arises with vertices only corresponding to free submodules. And the second motivation is that yes, it makes everything much more simple in our case. And we're now so I want to go over this example and try to do the same thing that we did earlier with the field, and we'll see that there is a little complication, which makes things a bit more interesting. So what happens now? So we want to calculate. Yeah, okay. So M is the set of all vectors A1, A2, A3. Okay, with AI from Z over 4Z. And the vertices, so lines. So what are lines? Lines are all the modules which are generated by one vector, but not any vector. So it's a set of all lines which are generated by a vector A1, A2, A3, but at least one AI is invertible. When I say invertible, I mean that it's not a power, it's not a product. Yeah. Oh, okay, yeah. In our case, it's just not two. So okay. So at least one AI is 1 or 3. Is 1 or 3. Okay, so for example, we can have 1, 0, 0, and 0, 0, 0. So this is a line. Sorry, 1, 0, 0, 2, 0, 0. Or in general, just I'll write it. What's generated by 1, 0, 0. Now, a non-example is what's generated by 2, 2, 2. This is also a submodule. It has two elements, right? 2, 2, 2 and 0, 0, 0, but it's not a free submodule. So we're not going to discuss this. We're not going to discuss only lines which have at least one coordinate in the generator being 1 or 3. And that means that the submodule has 4 elements, which is the same as the ring, and everything behaves nicely. The planes, so the planes will be all the submodules which are generated by 2 vectors. And now we need 2 restrictions. So any of the vectors v1, v2. So any of the vectors has an invertible coordinate. And moreover, we want the intersection here to not be large. We want it to be trivial. Again, why? We want this plane to be isomorphic to the ring squared. So the ring squared has 16 elements, right? It has in the first coordinate 4 options, in the second coordinate 4 options. And in our case, it suffices to it's enough. It's a necessary and sufficient condition for a submodule that's generated by 2 vectors to have 16 elements. In our case, to be a plane. So it's enough, and so it's enough to demand that v1, the intersection of v1 and v2 is just the 0 vector. Okay, sorry if it's too small. So these will be our planes.
Both of them, right?
Yeah, both of each. Okay, yeah, sorry, yeah, each. So each of the vectors. So for example, we can have the most natural example will be the plane generated by 1, 0, 0 and 0, 1, 0, but it can also be stuff more complicated. Now it's important. So this is an example. And again, a non-example will be the submodule generated by 1, 0, 0 and 1, 2, 0. So both of these vectors have an invertible coordinate, but when we look at the intersection of what's generated by this one and what's generated by this one, we see that 2, 0, 0 is in both of them. So they don't give us enough vectors, and it's not a plane. Okay, and now we want to ask what's the spectrum of this graph? And it turns out, sorry, what? Oh, okay, yeah, okay, sure. So how many vertices? Erase this thing. So how much time do we have? Okay. So again, this graph is bipartite. Maybe I won't yet state how many vertices there are, because I want in the remaining 10 minutes to like state the results that we have. In general, one moment. Yeah. Okay. So the number of vertices, the number of lines is p to the power of. Sorry. So it's. Okay. So in our case, it's lemma. Okay. The number of lines and planes in our Z over 4Z, okay, is 28 each. Okay. From where does it come from? This 28. So the general case, if we would have a general P and a general R, and maybe even a general D, so I won't say yet a general D, but we're a general P and a general R, then we would have P squared plus P plus 1 times P to the power of R minus 1. 2, sorry. P to the power of 2 times R minus 1. And when we insert P2 and R2, we'll get 28. Okay. So we now can define our last graph, and our last graph will be the projective geometry PD Z over P to the power of RZ is a graph, again, a graph whose vertices are free submodules of Z over P to the power of RZ D, so -1. Again, with edges corresponding to inclusion. Okay, so again, we have in exactly the same setting as in the field case. We have D-1 layers with each layer corresponding to a different rank of submodules, and we have some edges. And we're going to ask a few questions about this graph. Okay, so so I'll remove this. So again, we know that this graph, the full projective geometry is quite complicated. It's a D-1 partite graph. It's not easy to calculate its spectrum. However, we did notice that one can make things obviously much more nice if we look only at 2 layers in this case. So the projective geometry over dimension 2, right? It had exactly 2 layers because it has only lines and planes. And we're saying, okay, let's take only a specific set. So one can take a general couple of m and n dimensions, or we can choose our dimensions. And I want to state our results now. So if we take P to the power of D-1, the power of R. But so I'll write here 1 and D-1, take only the lines and hyperplanes in PD-1. Okay, so we have here an explicit calculation. So we have a direct calculation. So the spectrum of the graph is something I can write it down, but I'm not sure it will be very helpful to people. R-1 and the square root of, don't worry, the numbers here don't matter too much. Okay, so we have here a set of R+1 eigenvalues. We calculated also the multiplicities, which I didn't write down right now. What's important? What? Oh, sorry. So this is P to the power of D-1 over P-1, or 1 plus P plus P to the power of D. This is dP. I think it's called the P number, D or something. 1 plus P squared until we reach P to the power of D. Yeah, sorry. Please, yeah, here until we have. Okay, so here it's D-1, and here it's P to the power of D. Okay. So we have here so we calculated explicitly the set of eigenvalues.
It's like based on
Yeah, we have here one eigenvalue, 1 times R-1, and we have here R more eigenvalues, with the K running from 0 to R-1, the square root of P to the power of D-1 times K plus R. Okay. So the spectrum itself, K is from 0 to R-1. Yeah. So what's important here? So there are 2 important stuff. The result itself, what's important is that, again, the ratio, again, this shows that the spectral expansion of the graph is nice. Okay, that was the motivation. The nicer thing that I hope to show in the second part of the lecture is how we showed it. And what we did was to calculate we calculated explicitly the adjacency matrix squared, like we did in the field case. The matrix turned out to be a little bit more complicated, but still a very nice matrix. And it was pretty easy to calculate the eigenvalues out of it. But this is the first result. Okay, and the second was, okay, so we said, okay, we have here a very nice spectrum, and this spectrum turned out to be the same. Also, if we inserted here different rings, and then we said, okay, let's see if we can differentiate between two graphs that come from different rings. And then what we did was to calculate. So this is the first result. The second result was to calculate the automorphism group of the full graph. So we have p to the power of d minus 1 over p to the power of rz. And what we've shown is that the automorphism group is isomorphic to GLD of the ring with a semi-direct product of the ring automorphism group z over p to the power of rz. So we have GLD, which is the group of invertible of linear transformations of the ring, and we also have the ring automorphisms themselves. And we've shown so naturally, I'll show it also in the second part, hopefully, that each of these two actions induce a natural automorphism of the graph. And what we've shown is that any automorphism of the graph should be one of these two, should be some combination, some product of these two. And the third, recall that what we wanted, we started the spectrum we've calculated only for a very specific family of graphs. So actually what we've done, we can insert here instead of d minus 1, any n. So what we've proven was a little bit more general, but still it's not the full graph. So the third thing we've shown was that the automorphism group of p d minus 1, mn with mn, take any two layers from the full graph, is the same. Is isomorphic again to GLD, semi-direct product with the full graph. I'm sorry, I forgot to mention here, when we're looking at the full graph, we also have one reflection automorphism. So we should multiply here by C2. Okay, it's not too important here. The graph, if you recall, when we talked about lines and planes, then we have a symmetry. If we look at the projective case over a field, so we have a symmetry between the lines and the planes, right? At the final plane, for example, or over any field. So we can take like the inner product and look at the perpendicular, at the orthogonal subspace, which is a natural reflection, like taking lines to planes and planes to lines. And the same thing holds also in our case. So the full automorphism is GLN times the automorphism group multiplied by C2, which is the reflection. Here, when we take m plus n, so m and n, so it doesn't necessarily hold. Depends exactly on the m and n. But what's nice here in all the three results, and then I'll stop for a question for a few minutes. The third result shows that the automorphism group, also when we reduce ourselves only to two ranks, is still the same. Without the reflection, if an m and n.
But the low one is subgraph.
Right. And still the automorphism group is exactly the same. No, I mean, yeah, so we have the automorphism group. So we have two kinds of automorphisms. One that takes, let's say, lines to lines and planes to planes, and the second which takes lines to planes and planes to line, which reflects it. So the full graph, if we look at d minus 1 levels, we have a lot of levels. So again, we have one that preserves dimensions, and we have one that reflects dimensions. And I say when we're looking at an arbitrary m and n, so sometimes we can have a reflection if m and n are complementary, like in the case of lines of planes or line and hyperplanes. But if we take a general couple, we won't have the reflection because even the sizes won't be the same. Okay.
Suppose we take n plus 1 and n plus
equals 2 and D is something else.
Saying that the automorphism are reserved lines, right? In the two-dimensional subspaces, and you say that each automorphism like this can be extended.
Exactly. Yeah, exactly. So what we've done in let's say the third chapter, the third result was to show that not only any automorphism can be extended, but also the graph itself. Let's say if you give me 2 layers of the graph, the M and N layers of the graph, and I know the algebraic origin of the graph, then I can completely recover the graph. And a byproduct of being able to recover the graph, I can also extend any automorphism from the smaller one to the larger one, and thus it will be the same, the automorphism group. Okay, so these are the 3 results. No, so if we take M and N, the question was if we can take M and N to be equal. In that case, we will just have a discrete set. I mean, if we take only one layer, we will have a set of submodules without any edges. So we take M and N to be distinct. Okay. Any more questions? Yeah. So what we had. So I won't say cheated, but I made things much more simple than what they really are, because what we've shown, the example Z over P to the power of RZ is the simplest example, but we proved it over a more general case, like quotients of Dedekind rings over prime ideals. But in general, there are 2 key examples actually. So one is Z over P to the power of RZ, and the second key example is FPT over TR. So we're looking at the ring of polynomials with coefficients from FP, but only up to the power R minus 1 power. So these 2 rings are the same size. Both of them have P to the power of R elements. And what we've actually shown is that the calculation, the spectrum, doesn't really depend on the structure of the ring, rather only on P and an R. And that gives us that the 2 graphs corresponding to these 2 rings are isospectral. Not only are they isospectral, but the squared matrix is exactly the same, is isomorphic. Okay, so the first thing was to show that they are isospectral. And then we asked, okay, so if they are isospectral, are they also isomorphic? So that's what the automorphism group came for. So in this case, what do we know? So we know that the automorphism group of the first one is GL, say GLD, P to the power Z, P to the power of RZ, times the automorphism, the ring automorphism group of it. And the second, right, is exactly the same, but with FPT, or T to the power of R. Now, ring. So again, these 2 have the same size. Actually, GLD has the same size for any such ring. But the ring automorphism group is different, because Z over P to the power of RZ has no non-trivial ring automorphisms. Any ring automorphism has to take 1 to 1, but this ring has many automorphisms. You can take 1 to any other invertible element. To any element, not exactly, but there are much more automorphisms. Sorry, no, not 1, but this one, taking 1 to 1 also fixes any other element. In our case, in this case, 1 goes to 1, but when you ask where does P go to, so you can take P to any element which is divided by P. Like to any element, sorry, not divided by P, but to any element which has P as a coefficient, we can.
Let's give an example.
Yeah, okay. So here 1 has to go to 1, and here 1 has to go to 1, but when we ask where does T go to, so we can take, for example, to T squared plus T. And to any element which has T at the end, or at the beginning, we'll give a good ring automorphism. So at the end, we have that this one is size 1, this one has a larger size, and in general, the graph automorphism groups aren't of the same size. So in particular, they aren't isomorphic, the 2 graphs. Okay.
I have a very basic question in algebra that I don't know. Is it clear that these two rings have the same number of non-reversible elements?
So
Because then it's like, I mean, it's not clear to me why the two graphs all have the same number of vertices to start with.
yeah, so
Probably it is because of your statistical result, but I don't see it from.
Yeah. So maybe we'll do it in the second part. I'll explain for a moment why it is true. Okay. So any more questions before we go to break?
Any questions in Potsdam? We will wait for Felix.
Okay.
My name is Siegfried Beckles.
Okay,
Please, yes.
say it. I know that.
Going to make this effort? You're really going to cut out some stuff? Okay. My name is Siegfried Beckles, and we continue.
Okay. So we're continuing. So I wrote down the three results. I tried to do it like nicely with different colors, but afterwards I saw that on the screen on the Zoom, the green color is not very, it's not very comprehensible, so I won't use the green color anymore. But anyway, so I want to start with a few words to say about the first result. And as in the case with the field, if you remember, we described explicitly the squared matrix, the squared adjacency matrix. Again, we described only one portion of it, but it was enough, that portion. And what we did here was to do exactly the same thing, but it just turned out that the matrix was much more complicated. So I want first thing to write down the matrix. And again, I won't do it exactly explicitly. I will use it writing symbols, but instead I will write here numbers between 0 and r. So what I'm going to write here is the squared adjacency matrix when restricted only to lines. Well, again, we have lines, we have hyperplanes. We know from reflection or from the orthogonal map that the two portions will look exactly the same. So it's enough to describe this matrix. I will write here numbers between 0 and r. Take them to be representing different numbers. Okay, I will just we're going to discuss it. The next thing we're going to do is discuss what are these numbers. But first thing I want to show you the structure, the nice structure of the matrix. So what we have here is we have zeros along the diagonal. And then we have blocks of some size. Doesn't matter right now exactly what size. No, so I'm saying the numbers I'm writing here, take them to represent other numbers. You can imagine instead of zeros, I'll call it S0. Okay. So we have some number along the diagonal. Again, why do we have the same number along the diagonal? Because for any given line, the number of hyperplanes containing this line is the same. Okay. So we have here the same thing along the diagonal. We have now, we have small blocks around the diagonal which contain S0 along the diagonal and S1 everywhere else. Okay. Okay, and the same thing here. So we have blocks of the same size, even though it doesn't look like that in the picture. The blocks are the same size. And then again, we have larger blocks, each containing some number of blocks, having S2 everywhere else. Okay, again, the same thing. So it's a bit out of proportion, not exactly how one would like it to be. Okay, so let's say we have here squares. And then we have smaller, larger blocks, and then again, etc., etc. And then we have larger blocks containing these blocks having S3 everywhere else. And then we go like that, and then we zoom out until we get the whole matrix having SR outside all the blocks. Okay. Yeah, so I didn't explain yet what they are. I just want to show you like the structure of the matrix.
How do you fit together, like three, like?
Oh yeah. So again, I didn't yet explicitly write out the numbers. Okay. So if we turn again to the example, to the previous example, so we had p plus 1 along the diagonal and 1 everywhere else. So if we take R to be 2, so what will happen? So the matrix will stop at S2, and in that case, we will have S0. Lots of S0. Sorry, I won't write it this way. We will have blocks. Again, the number of blocks here isn't true to scale. It's more for the concept. So this is how the matrix will look for R equals 2. Okay. And then how do we calculate the eigenvalues out of this thing? So we notice that if we change the diagonal, which is an easy operation to do with respect to the spectrum, to eigenvalues, if we change the diagonal from S0 to S1, we get a block matrix, right? Blocks of this size. And here S2, it's a lot of blocks having S2. And then we can think of shrinking the matrix, taking each block and inserting only one coordinate. If you want, you can think of it as the inverse action to the Kronecker product with Jn. So what does this action do? So let's say we have a matrix, we have a matrix A, B, C, D, and we do the Kronecker product, Jn. Jn is just the matrix all ones. Okay? So the Kronecker product of A with Jn will just take each coordinate and insert a matrix of size n containing this coordinate. Okay, it's just the Kronecker product with Jn just inflates each coordinate from one coordinate to a block of size n times n. So what we're doing here is thinking intuitively, if we have a block matrix, what we can do is do the opposite action, like shrink the matrix, and each block take it and insert a coordinate instead of it. So what we will have here, let's say in this case, so we changed the diagonal from S0 to S1. And then we shrank the matrix and each block became one coordinate. So let's say, for example, so this block became one coordinate of S1. This block became one coordinate of S2. This is S1, S2, okay, S2. And so we have here a lot of S2s. And along the diagonal, S1s. And this is already something that...
What's this block S2? Is this a diagonal matrix now there? Is it diagonal small matrix, or is this a block of all entries?
Oh, so this block, everything here is S2.
Okay.
We had the diagonal, we had small blocks that everywhere else from the diagonal, it's S1s.
Yeah.
And then everywhere else that's not on the block diagonal, it's S2s. Only S2s. So now after changing the diagonal from S0 to S1, we have a block matrix, right? Because these
the S1s, you have S1s on the...
Yeah, I only changed the diagonal.
Okay.
First step, I changed the diagonal from S0 to S1. And then we have a block matrix, which has S1 along the diagonal blocks and S2 in all the other blocks. So now I take each block and shrink it to one coordinate. And then I get a matrix which has S1 along the diagonal and S2 everywhere else, right? It's a much smaller matrix because each block became only one coordinate. But then we got this matrix, which again is something that is easy to calculate. If we want, we can make S1 become S2, like again, change the diagonal, and then shrink it to something that's easy to calculate. Yeah.
Okay, so like technically how you frame them and so on, but like what does it do?
Okay. Yeah. Okay. So actually, the more formal way to do it, the way we calculate the eigenvalues, is the opposite thing. What we did was notice that we can start. Let's say we're working over S. You know what? Let's say we're working over R equals 1. Okay. So the matrix that we're aiming to get to.
procedure of describing calculating eigenvalue?
Yeah, so what I want to explain now is the opposite procedure, which lets us also calculate the eigenvalues. Okay, I'll give two examples, and I think it will make things clear.
The bit like what you're saying, is some kind of mechanism.
Yeah, yeah, exactly. Yeah, so we had two steps in let's say in the first result. The first one was how we describe the metrics in this way, which is something I hope to elaborate on in a few minutes. And the second thing was how from this matrix we calculated the eigenvalues. Exactly. So I'll now first show how we calculated the eigenvalues. So let's say we're working over R equals 1. So the matrix we're aiming to get to is, let's say, S1 with S zeros anywhere else. Okay, so we say,
Sorry, now I'm being pedantic. That's zeros on the diagonal, that's one of the diagonal.
sorry, yeah, you're right. Yeah, yes. So it's S0 and S1. So what we do is let's say we define the matrix G1 to just be S1, yeah. Or R, doesn't matter. A matrix with one coordinate. We know its eigenvalues. And then we define G0.
Yeah, this is a rank one perturbation of the diagonal matrix with S zeros. Basically.
Yeah, exactly. So what we do here is we take G1, the Kronecker product with Jn for some n, doesn't matter currently what n, Jn, and this gives us a matrix which is everything S1, and then we take plus S0 minus S1 along the diagonal, right? So this is how we get from S1. So what's important here is that these two actions are very easy with respect to calculating eigenvalues. Why is that true? Because when we do the Kronecker product of two matrices, the eigenvalue of the product is just all the products of the eigenvalues. And obviously adding addition along the diagonal doesn't really change, it just moves the eigenvalues. So let's say now I'll do another example which is kind of the same, but just it might help for clarity. So let's say we're now working over R equals 2. So again, we start G2 is going to be S2, and then G1 will be G2 times the Kronecker product Jn plus S1 minus S2 In. So after this step, G1 is this kind of matrix. S1, S1, and everywhere else too. And then G0, the final matrix will be take this matrix and inflate it. G1, the Kronecker product with Jn, it's actually different n, but it doesn't matter right now, plus S0 minus S1 In. So what this action does, the transition from G1 to G0 inflates each coordinate here to a block. And then we change the diagonal from S1 to S0, which will exactly give us this matrix. Okay, so what we've done is it's some sort of like recursive procedure, which starts with a matrix which an obvious unique eigenvalue, and then with these two actions which are being applied R times, we can get to our matrix, but with an easy way to describe its eigenvalues. What's important here, what makes stuff easy is that the eigenvalues of Jn are mostly zeros and n. The spectrum of Jn, which is the matrix which is all ones, is n, and then a lot of zeros. So this means that after every level here, we have all the eigenvalues from the previous level time multiplied by n, and then many more eigenvalues of the sort S1 minus S2. Okay, so that's how we calculated the eigenvalues out of the matrix. And now what I want to do is, so I won't explain I won't get into all the details of what we've done, but I do want to mention 3 important lemmas, which I won't prove all of them, I'll try to explain them, which gave us this description. Okay, so the first 2 lemmas are that lemma, take let let's say AB, B lines, okay? Then the number of hyperplanes containing both A and B depends only on, I'm going to explain in a second, on the isomorphism type A intersection B. So what do I mean by saying the isomorphism type? I have a line A, what will I, okay, so I can erase this. So I have a line A, which is isomorphic to Z over P to the power of R. What are the submodules of A? So when we're thinking of the submodules of A, it's the same as thinking of ideals of this ring. And that's the same as saying, we can say ideals. So if someone is not completely familiar with ideals and submodules, we can just say that the submodules of A are exactly of the type P to the power of I Z over P to the power of R Z. Okay, so if I want a set to be closed under multiplication by elements from here and to be closed under addition, it has to be something of the type P to the power of I times the ring. So I have R option. So okay, let's describe them completely. So one of them is, so one set is all the elements. The other is all the elements of the type P, 2P, until P to the power of R minus P. And then the second will be P squared, 2P squared, until P to the power of R minus P squared. Okay, so these are, and the last one, the smallest subset, the smallest submodule will be P to the power of R minus 1, 2P to the power of R minus 1, until we get P minus 1 times P to the power of R minus 1. Okay, so this one has P elements. The one above has P squared. This one has P to the power of R elements. This one has P to the power of 1 element, P to the power of R minus 2. And this one has P elements. And what I'm saying is the isomorphism type of a submodule is just which I do you choose here? Of which one is it isomorphic to? How many, if one wants to even simplify it even more, how many elements does this intersection contain? The intersection can contain only one element, 0. It can contain P elements, which is, in this case, it can contain P squared elements, and P third, and etc. If A and B are the same, the intersection will contain P to the power of R elements, right? So let's take an example. So
Here are lines.
Yeah.
Intersection could be more than one point.
yeah, exactly. So this is where our case changes or differs from the field case. Because for example, let's take A. So let's again, we'll work over D equals 2. So we have A is equal to the line generated by 1, 0, 0. Okay. So obviously, let's take B1 to be the line generated by 0, 1, 0. Right? So obviously, the intersection between them is only 0. This is easy. Let's take B2 to be the line generated by 1, P to the power of R minus 1 and 0. So we know that all the elements, so A, the intersection of A and B2 contains all the elements of the sort P0, 0, or in general, it will be everything that is generated by P0, 0, right? Because when we take this vector and we multiply it by P, then the second coordinate gets annihilated, and we remain only with the first, which is also an A. And again, and if we will take B3 to be, let's say, 1, P to the power of R minus I, P to the power of R minus J. So again, what will the intersection be? So when we multiply this vector by P to I, the second coordinate will be annihilated. if we multiply it by p to j, the third will be annihilated. So let's assume, let's say that I is larger than j, then when we multiply b3, when we multiply this vector by p to the power of I, we remain only with the first coordinate, and thus it will be also both in A and in B3, in the intersection of them. So what we have here is something very interesting. Instead of the field case, where the intersection of two lines has exactly one option, 0, here the intersection of two lines can be any of our options. It can be 0, it can contain p elements, it can contain p squared elements, and anywhere between the range of 0 and p to the power of r minus 1. And what we've shown, and it's very easy to show, is that the number of hyperplanes containing both A and B depends only on the isomorphism type of the intersection. And that means that, let's say, again, we're working with A, with this A, the nice one. We can think of it as what's generated by E1. So, okay, we'll call it A, we'll call it E1. And we now notice if we agree about the lemma, if you agree to accept it, if we accept the lemma, that if we take B1, let's say, to be the line generated by 1P0, and B2 to be the line generated by 1PP. So the intersection between A and B1 and the intersection between A and B2 will be the same size, right? So A, the intersection will be the same as A intersecting with B2. And this gives us that the number of hyperplanes containing both of them will be the same. Now, why is that important? Why is that interesting? Because the number of hyperplanes containing both of them is exactly the coordinate that will appear here in the matrix in the entry that corresponds both to A and to B1 or to B2. Okay.
What is isomorphism type?
So isomorphism type is
the dimension of the or the rank of
here it's not exactly a dimension or a rank because it's smaller than the ring itself. It's not like in the case of the field where it has to be a vector space itself. Rather, here, if we take the line A, then it has many submodules. For example, it has a submodule which is generated by the line P00. It has a submodule which is generated by the line P squared 00. Now we notice that this submodule doesn't have P to R elements. It has P to R minus 1 elements, and this one has P to R minus 2 elements. So when I say isomorphism type, I mean to say that A, the intersection of A with B, it's a submodule of A, right? So it's isomorphic to P to the I Z over P to the R. So this I, it determines the isomorphism type of this intersection.
But at the end, okay, so it's not rank or dimension, but it is like linear algebra in the sense that the number of elements of the submodule determines the isomorphism type.
Right. In our case, in our case of two lines intersecting, yes, exactly. The number of elements. If we go to higher dimension, it gets a bit more complicated. But in our case, yes, the number of elements determines exactly the isomorphism type of the intersection of two lines.
For this particular thing?
Yeah.
Is it the result? Like if you take another ring with the same. So now you're
No.
only on this model ring, right?
Yeah, we're working only over this. It will be the same for the second ring. And it will be the same in general for the general setting that we've shown. Like if we take O to be a Dedekind ring and we take a quotient by a prime ideal, everything will work the same as we're working here. There will need to be like almost no adjustment. I mean, when I worked, like when I thought about this stuff and when I played with it, so I did everything with this ring, with the ring Z over P to the power of R. And then at some point, I noticed that everything works exactly the same as for FPT over T to the R. And then I came to OA and we discussed it, and OA said, okay, so maybe we'll try to think about what's a general case that this will hold. And we noticed that it's a prime quotient of Dedekind rings. And then I said, okay, so I'll go over my notes and I'll change, like in cases where I said stuff that are only specific to the integer ring, I'll change it to the more general case, and there will be nothing to change. Like everything holds exactly the same. Yeah, prime powers. Exactly. Yeah, quotient by a power of a prime ideal. Yes, thank you. Okay, so exactly, yeah. Yeah, exactly. Like when we think of it geometrically, which doesn't exactly make sense, then we have here lines that in some sort are like shorter than the others, or they overlap themselves sometimes, and stuff like that. Yeah, exactly. Exactly. So again, so we have this lemma, which says that the number of hyperplanes containing both A and B depends only on the isomorphism type. And this lets us, so the second lemma will be, we calculated, so the number, so let's say for any A, for any line, the number of lines intersecting it by this submodule is fixed and depends only on I. Only on I. So what this tells us is that it doesn't matter with which line you start. So this actually lets us work only with a nice line, let's say this line, and then we do all the calculations over this line. And what the second lemma lets us do, this is a very simple lemma, it's very easy to prove. It lets us say, oh, okay, everything we did over A1, over A, also holds for any other line. So when we look at the graph, how it looks like around any vertex, it looks exactly the same. Okay, and the third, so what we know now, let's say, so these two lemmas let us fully describe the first line. The first row, sorry. So we have here a matrix, and let's say we put here at the first row and column A, okay? So at the first coordinate, we have some number, let's say S0. And then we have some number of lines. I don't know exactly, I mean, we do know exactly, but we didn't say it. We don't know exactly how many, but there is some number of lines which intersect A at the largest possible intersection. So this will put here S1. And then there is a larger set which intersects A at a little bit smaller intersection, etc., until we reach SR. So this is the first row. Now everything until here is very standard, is very simple. What we've shown, I don't know if to call it even a breakthrough because it's also simple itself, but the only non-trivial thing that we've done is the lemma is a basic lemma, which says that given, okay, so I'll write it, let A, B, C be lines. So the size of the intersection, let's say, of A and C is larger, I'm not sure exactly what's the direction now, but is larger than the minimum of the intersections. So in some sense, this gives us like the opposite of an ultrametric on this graph. So if I have 3 lines and I know the intersections of 2 of them, this lets me very easily give me some bound on the third intersection. And this let us very nicely completely fill out the matrix, because this let us say, okay, so I have here S1s, S0s, so we can reorder the elements in the first row to give us this nice structure. All right, so this is the first thing that we've done. And this was the main important lemma, which is based on the fact that we're working with lines. If we would take an arbitrary submodule, if we would take planes or hyperplanes or stuff like that, then this lemma wouldn't hold. And that's why in this theorem, in the first result, we have to have here 1. Because actually, again, like I said before, in our result, we could change d minus 1 to be any n. It wouldn't matter too much. It would make the result much less nice. So that's why I gave the result for d minus 1. But the 1 here is crucial, because the main lemma, which lets us infer from the first line. The rest of the matrix is based on the fact that we're working over lines. Okay? Okay, so I want, okay, so we have like to 1, to 45 or 50, 45, to 50. Okay, so I want in the remaining 10 or 15 minutes to explain what we've done in the next two results. So in 2 words, the second result, if we would exchange here the ring Z over P to the R and exchange it by the field FP, it's a very standard result. The result that the automorphisms of the projective geometry over FP is exactly the semidirect product of the GLD and the field automorphisms, in that case, times S times C2, is a standard result. It's not only a standard result, it's even called the fundamental theorem. Fundamental theorem of projective geometry. And what we've tried, and it's also in, I don't know if someone here is also in building theory, but it's also a standard result in building theory. What we've tried to do is, okay, let's see if we can generalize this result not only to the case of fields, but to the case of not exactly arbitrary rings, but to the rings that we are working with. And what we did was we took the notes. There are several proofs of the fundamental theorem of projective geometry. What we did was we took the lecture notes of, I'm not sure exactly who he is, someone named Putman, who has his notes. What? Oh, Putnam, yeah, sorry. Putnam, thank you. We took his notes, we took his proof, and I just like I went over the notes, and I tried, and I looked, okay, every space, every place that the proof failed for the ring case, we try to think, okay, so what can we do? What can we do instead to fill in what we need to fill in? And what was very nice is that when working over fields, everything just like falls into place very nicely. But when working over rings, then some stuff don't work. I'll even give just for an example, what he does in his proof is to prove that any line of the sort 1 something or 0 something, let's say that, okay, so I'm writing now a vector as a row, not as a column. So let's say a line is generated by this thing. We know that it has to be sent to something which is similar to the map here. And he said, okay, so that's enough, let's say. But in our case, it's not true, because there are lines that are not generated by a vector which has 1 at the beginning and not 0 at the beginning. If we're working over a field, then any non-zero coordinate which is here can be inverted to 1. But in our case, we also need to regard vectors that look like this, which have an other invertible coordinate. So this is just one example for stuff that work very nicely and very easily for the case of fields, but don't work so nicely for us. And what we've done, the major tool that we used was to infer from from graphic aspects of the graph to algebraic aspects of the graph, and vice versa. So we know that the graph has some algebraic origins. We can use them, and when we're analyzing the algebraic aspects of the graph, we know that it also has some graph theoretic aspects, so we can use them. So I want to give an example, actually not on the second result, but at the third result. So what we've done at the third result, yeah, exactly, yeah. Yeah. So the third result was to see what can we say about smaller graphs. So what interested us in the beginning originally was this family of graphs of the kind 1, comma n, because we wanted to show the isospectrality but not isomorphism. But then we saw that things can be generalized to an arbitrary m and n. And what we've tried to do was to show that knowing the graph, knowing 2 layers of the graph, knowing the first layer and the nth layer of the graph, we can completely recover the whole graph. And in a similar way, that lets us also extend any automorphism of the smaller graph to an automorphism of the larger graph. And then we can easily construct a bijection between these 2 automorphism groups with the one direction just the restriction map, and the other direction the extension map. Again, except the reflection, which holds only if M and N are complementary. But if they are not, then we don't have the reflection. So I want to give you an example of how to extend it. Let's say we have the first and the nth layer, given two layers, 1 and n, how to reconstruct the second layer. Okay, so what we have is a graph whose vertices, it's bipartite, it's easy to distinguish between the vertices corresponding to lines. So these are lines, these are n spaces. And by saying in n space, I mean modules that are isomorphic to the ring to the power of n. And we want to recover all the planes. What do I mean by recover? So we both need to know how many vertices, we need to construct the vertices, and we need to know how to connect them, right? That's what we need to do. So we're saying the following. I want to go over, let's say, iterate. So step 1, iterate. I hope it's the right word. Iterate over all doublets AB of lines. Okay? And what I want to ask is A plus B a plane? If A plus B is a plane, I will add a vertex corresponding to A plus B. But if A plus B is smaller than a plane, which happens when the intersection is larger, then I won't add a vertex. And how do I do it? How do I know if two vertices, I'll mention one more thing, if two lines, their sum is a plane, then I know that there is exactly one plane, one vertex, which is connected to both of them, right? If the sum is smaller, then there will be several planes containing them. So what I will want to do is for any two lines whose the sum is a plane, I'll add one vertex here in the second layer and connect it to both lines. And how will I know if two lines, their sum is a plane? So this is easy. I can check how many n spaces are connected to both of them. And by the lemma that we've shown earlier, the number of n spaces connected to both lines A and B determines to us what's the isomorphism type of their intersection and their sum. So if there is some number, let's say x, n spaces containing both, so we now won't use the words containing, but connected to both A and B, add a vertex in the second layer. And then where do we connect this vertex? We connect it both to A and to B, and to all the n spaces that contain both A and B. Right? Because any n space containing both A and B has to contain also A plus B. But now we added many more vertices than we should add, right? Because let's say the line, these two lines, and these two lines, if P isn't 2, these two doubles construct the same plane. So I need some way to identify between these two planes. So again, how will I identify? I will say two planes are the same if the set. Okay, so here it becomes a little bit more complicated. I will say it in a bit simplified way, which is not exactly true. But two planes are the same if they are connected to the same set of n spaces, right? So, or to the same set of lines. So there's another step, which I will now skip because it's a bit technical, but there is a way to, given a plane, to connect it to all the lines that are contained in it, or to connect it to all the n spaces contained in it. And then after I do that level, I can merge all the planes that are connected to the same set of lines or to the same set of n spaces. And this gives me, given two layers, the first and the nth, I can completely recover the second one, given not too much information. I just know how many n spaces contain each couple of lines, and according to that, add planes accordingly. So this case is, so we have this case. We also need a way to add layers above n, which is a bit more complicated. And if we take, instead of lines and n spaces, we take m spaces and n spaces, it becomes even a little bit more complicated. And there is a very technical lemma which we needed to show, which was little bit annoying, but not too much, to show that stuff work. But again, given m and n layers, we can easily reconstruct everything in between. We can reconstruct everything above n, and we can reconstruct everything lower than m. And using these steps just iteratively, we can easily reconstruct, not easily, we can reconstruct the whole graph and thus extend also any automorphism. Okay, so I'll stop here. Maybe I'll just mention one more, like a final word. What's nice, what I found appealing about this research is really about the nice interrelations between the graph aspects of here. Like we can see the number of n spaces, the number of vertices connected to a couple of vertices tells me algebraic information about the lines that are represented. And on the other hand, you can also, from algebraic information, we can infer a lot of stuff in the graph theoretic module. So it's I don't know, it's very cool because it lets us fill in a lot of information that, I don't know, in the field case, it's very easy. We just get it like almost for free. And when we're working over rings, that stuff don't work so simply. We have this tool that lets us fill in the information that we don't have. Okay, so I'll stop here. Thank you very much.
Thank you very much.